Alright, hello, my name is Marquis Lindsay. I will describe all the methods of integration discussed in my 112 CMAT class of April 1st, 2014. I will also demonstrate when to use each method and show you how more than one method can be used to integrate a function. Okay, the methods are first, use substitution, integration by parts, trig integrals, trig substitution, partial fractions, and improper integrals. Alright, let's go. Okay, the first we have use substitution. This method is the opposite of the chain rule. And the chain rule differentiate compositions of functions such as having the function 3x plus 1 to the second power. Okay, the chain rule will take the derivative of the whole function, which will be 3x plus 1. Okay, and then after that, they will times it by the derivative of just the inside. The derivative of the inside function is 3. This will equal 6, 3x plus 1. Okay, now use substitution is the chain rule reversed. And here we go, the integral of f g of x times g of x, g prime of x dx equals the integral of f u du. And now we will apply this to a problem for u substitution. The integral of, let's say, 3x squared plus 2x e to the x cubed plus x squared dx. Okay, now with u substitution, you will know when to use it when you see one function is the derivative of another function. And we will use u as the function that's the u in the du. Okay, so now if you see x to the 3 and 2x this is the derivative of this. So we have u equals x3 plus x squared. Du equals 3x squared plus 2x dx. U equals now we will apply the u. So this will equal the integral of 3x squared plus 2x e to the u dx. Okay, now our du right here, we actually have this in our function. So we will take it out, the integral of e to the u du. And we will always add a constant in case we lost it during doing the derivative. Okay, now we will bring this over here and plug our u back in right there. So this will equal e to the x cubed plus x squared plus c. And this is one example of how you use u substitution to get an easier function from your first function right here. We will start off with this integral. Integral of 3x ln x dx. Okay, now when we see this, we would think, what should we use as our u? We don't know, so this is what you will have to do, okay? Bring the ln to the top, the x ln to the top. That will make the integral of 3x ln x -1. Okay, now ln x is our inside function, and when we're using U substitution, we always have to remember our slogan, liate. If you're confused on which one to use as your U equals, so we can plug it back in and find the easier function. Liate, this means ln first. Always choose your ln first. It's sort of like PEMDAS as we learned in high school. PEMDAS. But liate is ln, your inverse function next. If you don't know which one to use, your algebraic, your trig functions next, and always last you use your exponential functions as your U. Always remember that. Liate is sort of like PEMDAS, but it's ln, inverse, algebraic, trig, and exponential. Okay, so ln comes first on our liate chart, so ln x is going to be our U. U is ln x. Our derivative of ln x equals 1 over x. dx, always. Okay, now we take this function right here and plug it back into our original function. That will make the integral of 3, take our constant out, as we always should. That's going to leave 1 over our u. So that's going to be u. And we have an x right here, x dx. X dx is right here, x dx, so that's our du. So 1 over u, du. See, right here, our du, we have an x and dx, so they cross out, and they cross out right there. Okay, so we have our du, 1 over u, 3 du. Okay, now we plug this in. This identity right here, as we should know, is ln. 1 over any constant is ln of that constant. So that will equal 3 natural log. And our u, ln x, is 3, the natural log of our u. Our u is ln x itself, plus c. Remember, always plus c, because we might have lost the constant during our derivative. For u substitution, we will use the integral with limits. With limits. Okay, we will use 0 and -1 of x to the 3 square root of x4 plus 9. Always have dx. Okay, this integral right here, okay, we don't have no inside function to use as our u, so we would have to bring this square root of x to the 4th plus 9 up to our numerator. So this will make it equals the integral of x cubed x to the 4th plus 9 to the -1/2 dx. Okay, now our inside function is our u. So our u equals x to the 4th plus 9. du equals 4x cubed. dx as always. Okay, now for our du, we have a dx and an x cubed, but we don't have a 4. So we have to take our 4 out by dividing by 4, divide both sides by 4 as we know. So this will make it equals 1/4 du equals x3 dx. Okay, now we take our original function right here and plug it back in using our u. So this will equal now integral of 0 to the -1 x3 u to the -1/2 dx equals 1/4, as we plug our du in, 1/4 integral 0 -1 u to the -1/2 du. Our 1/2 du equals x to the -3, so that's how we cancel these out right here. We have 1/4 du in place of that. Okay, now as we get here, we have to use our power rule, and then after that we have to enter our limits to get back to x. We can't use u to solve the problem to get a definite integral, so we have to get back to x. And right now, we will raise 1. Power rule, as we know, you raise 1 plus 1 by whatever you raise it to, times it by the reciprocal of that. So this is plus 1, so it's going to equal 1 over 4. That plus 1 is 1/2 times the reciprocal of 1/2. That's going to be 2 u to the 1/2 dx. No. Gotta take that. Right? Gotta take that part. Alright. So this is going to equal now. This is going to equal 1 over 2 after we multiply these two. 1 over 2 x to the 4th plus 9 to the 1/2. Now we're ready to enter our limits. We're ready to enter our limits. Okay, now we're going to enter our limits over here. Okay, now our limits are about to be entered. 1/2. And to your x, our first limit is 0. 0 to the 4th plus 9, 1/2, minus the bottom limit. Now we do some simplifying with each side. This will be 1/2. This is the square root of 9, which is 3. This is -1 plus 9, so this is going to be the square root, negative square root of 10. That's our answer for substitutions with limits. So first, we find our inside function, make it our u. We plug in our u, we plug in for our u, we make our du, right here, plug in for our u, make our du. Then we do our power rule, because we see we have a constant raised to an exponent, so we do our power rule, plus 1 divided times the reciprocal of whatever we get after we add that 1, right here. Then we plug for what we found that's our u back in. And then that's when we enter our limits and get back to x. Enter our limits, and here we go. Final product. An easier function from this, and this. This to this. All right, that's it. Next we have integration by parts. Okay, with integration by parts is the reversed product rule. Okay, and this how we apply it to look. The product rule looks like this. The integral of f of x, g prime of x, plus g of x, f prime of x, dx equals f of x, g of x. Okay, this is the product rule, and now we have to solve for this function all the way on the left to make our integration by parts function. This would be f of x, g prime of x equals f of x, g of x minus g of x, f prime of x. Then we have to distribute our integral to each one of our functions. This will need an integral, and this one. Did I get that right, bro? Let me see. Yeah, still recording, bro? Okay, now this is our function right here for integration by parts. we're going to use this to apply it to one of our functions. Now here, this is our function right here. F of x, g prime of x dx equals f of x, g of x minus the integral of g of x, f prime of x dx. Okay, now our u in integration by parts equals f of x du, as we know, is f prime of x. Our dv equals g prime of x, and our v equals g of x. Okay, so now we have u, du, dv, and v. Our f of x is the integral of u times dv equals u times v minus the integral of gx times f prime. Bro, you think I should write it first and then say it? That's what I should be doing. Okay, so this is our product for our integration by parts. F of x g prime of x dx equals f of x times g of x minus the integral of g of x times f prime of x. And here we go. Right here, our u equals f of x and our v equals g of x. So it's u times dv equals u times v minus the integral of g f prime of x. Okay, now I will give you an example of how to apply this function. And when we do it, we always will time u Okay, now when we do this, we have to times u times v, and after that, v times dv. And you see that right here. U times v minus the integral of v times du. Now we're going to apply this right here. We have the integral of x cosine x dx. This will... Okay, now we have the integral of x cosine x d of x. We know when to use this because we have two functions multiplied by each other. Neither one of them have an exponent or anything. So when we have two functions multiplied by each other, we have to use one of them as our u. So our u will equal our first function in this, that's our x, and our derivative of x is just going to be dx, 1 as a constant somewhere in here. Our dv is going to be the rest of the function. dv equals cosine x dx, and our v equals what you will know when to find our v, because what's the derivative of what makes cosine x? What makes cosine x's derivative is sine x. So now when we have this, we have to plug it into our formula right here. Our u is derivative of x cosine x dx equals u times v, u times v, u. Okay, now we have u times v minus the integral of v times du. V times du. Our v is sine x, and our du is dx. So we will solve for this function right here. This will equal x sine of x minus the integral of sine x. That's negative cosine x plus c. we always will plus c because we might have lost it during our derivatives. Okay, and this, as we simplify, it will be x sine x plus cosine positive, and 2 negative makes a positive, cosine x plus c. This is our final product.
Like this.
Okay, now we have trig integrals. Our first identities are integral of tan squared x dx equals the sine over cosine, as we all know. And we will bring the cosine to the numerator. That will make our cosine in parentheses. So cosine squared will be our x, our u. Okay, now our other identity is sine squared x plus cosine squared x equals 1. So we're looking for solve for sine squared x, we will minus cosine, so it will be 1 minus cosine squared x. We'll solve for that, just bring it over to this side of your equal sign. Same with this, tan squared x plus 1 equals secant squared x. So if you're solving for tan squared x equals anything, it will be secant squared minus 1. Same for cotangent squared x plus 1 equals cosecant squared x. Okay, and same as this, sine squared x equals 1/2 the 1 minus cosine squared x, as we see right here. 1/2 1 minus cosine squared x, same as right here, we solve for sine squared x is 1 plus cosine squared x. And sine 2x equals cosine x, sine x, and tangent squared x is secant squared x minus 1. And then we do the antiderivative of that, and the derivative of secant squared x, the antiderivative is tangent x minus x. The antiderivative of 1 is x. We go back to x. Okay, now if we have a function and one of our coefficients is odd, and we have sine and cosine, this is what we do. We have to save the odd, one of the odd functions and make it as our dx. So we would say take one of these, this is the odd one, take one of these right there, put it as our dx, it equals our dx. So we have sine squared x, cosine squared x. So when we do our derivative of that, we solve for this, that's 1 minus cosine squared x, and our dx is over here. Okay, our inside function is our cosine squared x, so we make this our u. Our du will be negative sine x dx. And we come over here, and now we take this function right here and plug our u's in. So we have minus 1 to the integral of 1 minus u, because cosine squared x is our u, so we plug our u in, our u squared du. We solve for this. Now we have to do our power rule right here. We distribute your u right there. And now we have to do our power rule. When we get this, we do our power rule, plus 1, we get u to the 3 over 3. You do the power rule plus 1, divided by whatever this number is right here, over here. And you always plus c, because you don't know if we lost the constant. Now when we have this function right here, we have to plug our u's back in. From right here, we have u equals cosine squared x. So we have minus cosine cubed x over 3 minus cosine to the 5x over 5 plus c. This is our function. Alright, I'll write it up. Cosine when they're even. Okay, if a function is even, we just use this identity that we have right here. Cosine x equals 1/2, 1 minus cosine 2x. Comes from this right here, that first identity. So cosine x dx equals 1/2, 1 plus cosine 2x. Okay, our u is our inside function. That's going to be 2x, or du is the derivative of that, 2 dx. Divided by 2, because we only have a dx, we don't have a 2 in this function. We divided by 2, so it's going to be 1/2 du. 1/2 du right there. So we keep our 1/2, and we have to integrate this. Integrate 1 equals x, plus the integration of that is 1/2 sine 2x, plus c equals then we distribute our 1/2 into our function, times it by each one. It's going to be x over 2 plus sine 2x over 4 plus c. We always add the c in case we lost a number, a constant in our derivative. Damn, how fast was that? Okay, now this is an example when sine, cosine, or tangent are odd and secant becomes even. We always have to remember that tan squared plus 1 equals secant squared x. That's our first identity that we went over here. Right here, we always have to remember our identities. Okay, now to find this, secant to the 4th, secant is even. So what we do, we save one of these secants to make it secant squared. That's going to be our du. Okay, so we have secant squared, tan to the 3x. We bring that down, and our dx. And the derivative of this is tan squared x plus 1. Secant squared x equals that. So that's how we get that. We bring this down, and our du right here, that was our saved function from the beginning. So now we plug our u in. Saved function, the antiderivative of secant squared x is tangent. Because tangent weak, secant squared x. Okay, now we plug it in, u squared plus 1, u to the 3x du, and we have to distribute this u3 into this function. Makes it u to the 5 plus u to the 3. Now we have to do our power rule, plus 1, and divide it by whatever this number is right here. So plus 6 is u to the 6 divided by 6, plus u to the 4 divided by 4. Now we plug our u in, as we dump over here. Tangent x is our u, so now we plug it back in. Tan to the 6x divided by 6 plus tan to the 4x divided by 4 plus c. And always keep your c because you might have lost it during the derivative. Okay, now we have trig substitution. And these are our identities for trig substitution. If we see a squared plus x squared, that's going to be x equals a tangent of theta. X equals a sine of theta if we see a squared minus x squared. And x equals a secant of theta if we see x squared minus a squared. Sign reversed. Okay, now this is an example triangle of how we set it up. Okay, if x equals a tangent of theta, that's when we have x squared plus a squared, as we see right here. That's when we have to solve for. We have to solve for tangent of theta, so we can find the tangent of theta. We multiply a by both sides, so that's going to be x over a equals the tangent of theta. And tangent of theta, SOHCAHTOA, as we all know, SOHCAHTOA, tangent is opposite over adjacent. So we have the opposite angle of theta, x over a. Okay. Now here we go with our first example. We have dx over the square root of 4 plus x squared. Okay, now as we look over here, if we see a plus x squared, that's when we know we have tangent. Okay, so to make this squared, as we have to make our a squared, 2 to the second power is 4. So we square that off. Okay, so now our x equals a, our a right there is our 2, so 2 tan theta. And our dx, as we know, the derivative of tan theta is secant squared. So we have 2 secant squared theta, d theta. Okay, now to solve for this problem, we have to find, we have our top right here, but we don't know what this is, so we have to solve for this square root of 4 plus x squared. 4 plus x squared. 4, okay, so we have 4 plus our x right here is 2 tan of theta, 2 tan of theta squared. Right there, so now we come down, we distribute this 2 to each one of those inside that, so we have 4 plus 4 tan squared of theta. Okay, now we have to factor one of these 4's out of here. So now we get 4, 1 plus tan squared of theta. Okay, now when we do the derivative of this, as we see in our identity earlier, tan squared x plus 1 equals secant squared of theta. So tan squared x plus 1 equals secant squared of theta. We have our 4 secant squared of theta right here. Okay, now our square root of 4, as we know, is 2, so we have 2 secant of theta equals 2 secant theta. Alright, now we have to, okay, now we solve for this, so now we plug our dx in and what we solve for our square root of 4 plus x squared. Okay, our dx is 2 secant squared. Right here, we plug that in, and that it came out to be 2 secant theta. Right here, so we plug that in, we get this, and we factor these out. We have 2 of these, 1 of these, so that give us 1 of it. 2 minus 1 is 1, so we have a secant theta d theta. Our d theta always comes with this. Okay, now this. Okay, now we have to find the antiderivative of this. What gives us secant theta? Secant theta, as we all know, is the natural log of secant theta plus tan of theta. The derivative of secant theta, tan of theta is secant theta. Okay, as we all know, our x is 2 tan of theta, as we found earlier. We solve for our tan of theta, so we can write our triangle, our special triangle. So we have x over 2 equals tangent of theta. Tangent of theta, substitute, opposite over adjacent, x over 2, so this is our opposite of theta, and this is our adjacent of theta, 2. Okay, so now we have found our tangent of theta. Okay, we have that, but in our function, we have the natural log of secant of theta, so we plug in, and we know cosine is the reciprocal, secant of theta is the reciprocal of cosine, so cosine of theta is adjacent over hypotenuse, 2 over our hypotenuse right there, flip it, and that's going to be our reciprocal of secant of theta. So right here we have the natural log of secant of theta is the reciprocal of that, square root of 4 plus x squared over 2 plus tangent of theta. We already know x over 2. X over 2 plus c, we always keep our c in case we lost it during our derivative. Okay, now we have the natural log of x times square root of x to the 2 divided by 2. Let's see. Okay, this is partial fractions. Okay, partial fractions, they will break down the decomposition for each polynomial of this. Okay, this is an example of this right here, as we have x minus r if there is more than 1, and we have x minus r to the 5, that's how we label it, over 2, go. Okay, decomposition for x over this right here, a over this plus b over the second one. Okay, decomposition for this one right here, as we explained right here, is a over the first one, b over the second one, put it in parentheses and label them as their number come, c over x plus 1 to the third, d, this is only 2 of these right here, so we label the first one, then put number 2 as we keep going with our alphabet. Okay, example on the next one, x squared, okay, we have a linear factor. So when we do this, we put ax plus b, since we don't just have x over there. Over the first one, we have 3 of these, so we keep going with our alphabet, cx plus d to the second, ex plus f to the third, gx right here, we have 2 of these, so the g over that, and h, we make that 2, and we only have 1 x squared minus 1. Right here, x squared minus 1. Okay, that's it. Proper integrals. Okay, with improper integrals, this is how a normal graph will look with a proper integral. Neither one of the sides will ever go to infinity. But an improper integral, when you get past 0, b will keep going. It will never touch 0, but it will keep going all the way to infinity. And this is our natural log graph right here. We're going to use that later. Okay, so we have an integral with the first limit being infinity and our second one being a. This is how a regular function will be set up. Function of dx equals the limit as b approaches infinity. And we will write it on our line like this. A0 infinity, okay, as b approaches infinity, a to b right there is equals f of x to dx. Okay, so this is our example right here. Our limits is 1 to infinity, 1 over x squared dx. Okay, so now we will write our limit as b approaches infinity, as we wrote it earlier. If we have infinity right here, we have 0, and we have a and b as b approaches infinity, 1, from number 1 to b. Okay, now we have to do the antiderivative of this, so that we'll bring this to the top of to the numerator. That'll be x to the -2 dx equals the limit of as b approaches infinity will equal the natural log of -1 over x. Now this is where we enter our limits. Now you do your top limit minus your bottom limit. So we take this function right here, -1 over our top limit is b minus our bottom limit. That's 1. After we simplify it, this is what we get, -1 over b plus 1. Okay, when we do that, 1 over any constant is 0 plus 1, that equals 1. Then it converges because it's a real number. Okay, diverge means it's infinity or do not exist. Converge means it's a real number. If one of these functions converge or diverge, that's what it is. If one of them diverge, the whole entire function is divergent. So if we get this 1 right here, we can come back to our original function and write 1 over x squared dx converges. And that will be our answer.
It's me